particularly Poonam, for inviting me to visit this famous university for the first time, and also for giving a talk in a condensed matter meeting for the first time. So I am basically high energy physicist and try to give something new which we recently worked called singular value topology. This is based on this paper in this year. This is my student Gaurav, and this is my collaborator Ranjan in IIT Tirupati. Okay, so topology, as you know, is very important and most vibrant areas in condensed matter and quantum physics. On the other hand, the rise of non-Hermitian physics makes a paradigm shift in all corners of physics. Non-Hermiticity gives a very interesting topological phenomena which is different from that of in the Hermitian physics. Particularly in non-Hermitian system has complex energies, and they integrate structure like knots and links, collection of knots in complex plane as the system parameters are varied. So it will be exciting to establish a link between the topology in Hermitian system and non-Hermitian system, and this talk is we are going to explore that possibility in this talk. So this is a plan. So I'll very brief introduction I'll give in non-Hermitian physics, because I am working non-Hermitian physics for a long time, and also then I'll talk about few works in knots in non-Hermitian systems. Then I'll come to this singular value decomposition and biunitary transformation, how a complex matrix can be diagonalized by a biunitary transformation in contrast with the unitary transformation. Then we'll come to this emergence of Hermitian topology from non-Hermitian knots. This is the main part of our work. Okay, so very quick review. So on non-Hermitian, so we'll start with the consistent quantum theory, a theory we call consistent quantum. If it has the four basic properties, that real eigenvalues and orthonormal eigenfunction complete set, positive definite norm, time evolution, unitary time evolution. But I just want to make one comment that I'll be using Hermitian word, Hermitian and non-Hermitian, which is not appropriate word. It should be the non-self adjoint or self adjoint. There is a difference between these two, but commonly people use Hermitian and non-Hermitian, so I'll also be used, but that is not proper word for this. Okay, so the framework of quantum mechanics has been extended by relaxing the constraint of self-adjointness by following two categories. If the system is PT symmetric, or if it be a bigger class introduced by Bender in 1998, pseudo-Hermitian, a bigger class of PT symmetric system introduced by Ali Mostafazadeh in 2002. In two categories, this lead to a consistent quantum theory that if the PT symmetry is unbroken and this S operator is a positive definite operator. Of course, there is a problem that we'll talk little later, that presence of exceptional points or spectral singularity. In this time, it's a villain that they will not allow to have a consistent quantum theory. But of course, non-Hermitian theory is not started with Bender works in 1998. This has a very rich history. People like Dirac, Fermi, they did work on non-Hermitian theories in 1940s. Okay, so this will have a consistent quantum theory with non-Hermitian system in a modified Hilbert space, and that Hilbert space is modified with a CPT inner product. C is an additional symmetry of the theory associated with every PT symmetric system. There is a C symmetry. So if you modify your inner product with the CPT inner product, so we consider the non-Hermitian theory in a modified Hilbert space, which has not the Dirac inner product, conventional one. We have a CPT inner product, then we'll have all four basic properties satisfied. Similarly for pseudo-Hermitian theories. More later, people put all these things in a better framework, which is bi-orthonormality and G inner product. So I skip over. So bi-orthonormality, that H and H dagger are not same, so they will have a different set of eigenfunction. So instead of normal orthonormal condition, we use a bi-orthonormal. So left are the eigenfunction of H dagger, right is the eigenfunction of H. So they together form a bi-orthonormal set, and the completeness also. And these are related by a metric operator G. So if we have a modified Hilbert space with G inner product, then we can have a consistent quantum theory. So by this way one can construct G. And we talk about people concerned about the physical observable. So a quantity will be observable if O dagger G is GO. So that are the good observables. Exceptional point, that non-Hermitian degeneracies where two or more eigenvalues and their corresponding eigenvectors coalesce simultaneously occurs in open system with gain and loss and described by non-Hermitian Hamiltonian. Basically the system matrix becomes defective, cannot be diagonalized because of the presence of these exceptional points, and it has many important role and associated with very rich physics, so plays important role in understanding phase transition, topology, sensing, photonics, quantum technology, wave engineering. So now exceptional point become villain to hero. Okay, so now come to the knots. I don't need to introduce knots. Knots means this, but mathematically it's a embedding of a circle in a three-dimensional Euclidean space. And it's a branch of mathematics where we study properties of mathematical object known as knots. Of course, it was introduced to describe the atoms in 1867 by Kelvin. That this proposed model for atoms are vortex ring circulating in ether and different elements corresponding to different knot structure. His student first tried to catalog this in terms of like a periodic table, but this model was abandoned as the ether was ruled out. But these are the knots classification that if you have, depending on how many crossing you have. For example, if you have 0 crossing, this is only one type. If you have 3 crossing, only one type knots is there. On the other hand, if you have 5 crossing, there will be 2 different independent knots, and in this way there are more than 35 crores knots known today. And the challenges in that, how a general knot can be unknot. So that is the challenge, open challenge actually. But of course, I'm not going to do this theory because in this work, we need only 3 simple knots. So this is Ehrlich, that suppose you have 2 eigenvalues, then they are not entangling each other, or if you have the eigenvalues in a evolve in this way and then you take a projection, there will be 2 separate circles. So this is we call unlink. And similarly, if you have the 2 eigenvalues evolve in such a way that we have this circle, then we call it is unknot. And if they entangle each other like this, 2 eigenvalues, then this is called Hopf link. And this is taken from this paper. Okay, so now I come to some review, some work already known in the knots in non-Hermitian theory. So this is the very first and very important paper. That figure was taken from this paper actually. So in 21. So in this paper, knots tried by the energy eigenenergy string provide a complete topological classification of one-dimensional non-Hermitian Hamiltonian separable bands. And this transition in this paper, they work that 2 distinct knots occur through the exceptional point. So I'll explain later, we'll see that all this previous work, the transition happens through exceptional point, and our finding is different from those. This is the first paper where the Hermitian topology and non-Hermitian, they are connected. So in this work, all the fundamental concept of chiral symmetric topological phases have the non-Hermitian origin. Basically, they said the non-Hermitian topology is the building block for Hermitian topology. And they find some identity equating the linking number between knots and the non-Hermitian bands. Again, the knot transition occurs through the exceptional point. Okay, and this is another work by Japanese group. They are very strong. They have very strong groups in topology and non-Hermitian topologies. Again, they try to connect the non-Hermitian topology with the Hermitian one and get some exciting results. So there are a couple of experimental papers to realize the knots in through experiment. So I'm just not going to these papers. So okay, now I come to the singular value or decomposition method. So singular value decomposition is fundamental factorization technique in linear algebra for any real complex matrix of m cross n, not square matrix, can be factorized in this way, where U is a unitary matrix, sigma is a m cross n diagonal matrix, m cross n diagonal matrix, and V is another unitary matrix. So these eigenvalues, these diagonal elements of these sigma matrices are known as the singular values. And V is this n cross n unitary matrix, U are the column of left singular, V is the right singular vectors of M. Okay, by this, using this approach and this, we can diagonalize any non-Hermitian matrix through bi-unitary transformation. So suppose M is a non-Hermitian matrix, it can be diagonalized by not by unitary matrix but by unitary. Two different unitary matrices are used to diagonalize this. So this is very simple proof. I'll go through in next slide. But if M is non-Hermitian, M dagger is Hermitian, which can be diagonalized through unitary transformation SS dagger, where MD square, because eigenvalues of MD, so it's MM dagger. S is of course unique up to a phase, and this kind of analysis is used in studying CP violation in high energy physics, and where this phase matrix has important role. Okay, so here is that proof that okay, so suppose I have a non-Hermitian matrix M, and then I design a H which is S dagger MD of S MD S dagger, and this can now it can be shown that if I consider a V matrix which is N inverse M, which is a unitary matrix, where it is so. Then if we substitute, use this equation and substitute, and then we find that a non-Hermitian matrix can be diagonalized by a bi-unitary transformation, that is through two unitary matrices. Okay, and this T is V dagger. Okay, so now we come to our formulation. So what we did, we consider a Hermitian Hamiltonian where this lattice momenta between 0 to 2 pi and n cross n. With the eigenvalues greater than 0, we need a positive eigenvalues. And it has also a topological transition. This is a Hermitian system which has a topological transition. And then we consider this is constructed out of two non-Hermitian A dagger, which we can always, because this is a Hermitian. Now A can be constructed using the SBD as this with the sigma V dagger, where sigma is the eigenvalue, square root of the eigenvalues of this matrix H. So using unitary matrix constructed out of this is the square root, sigma has the square root of the eigenvalues of H. So H is a Hermitian model which has a topological transition. Now we construct a non-Hermitian matrix whose singular values are the square root of that Hermitian. Okay. Now we calculate the winding number and of this non-Hermitian matrix. This is the usual definition. This trace subtracted, half of the subtracted to have a correct reference energy to compute winding number. And we found that this unlink phase is for nu equal to 0, unknot phase is for nu equal to 1, and Hopf-link phase is for nu equal to 2. So typically the knot transition always accompanied by EP, that all these papers, non-Hermitian topology papers, we find that always accompanied by, but in our work we'll find it's otherwise, because if you suppose, if you consider at least for 2 by 2 we have shown it explicitly, for 2 by 2 say at the transition point U1 U2 is say epsilon. So if you take then E or A matrix is epsilon to the power half times unit matrix and U V dagger, and similarly A dagger is like this, and they commute. So they can be simultaneously diagonalized, so there is no AP. Okay, now we consider the simplest possible topological model, which is one-dimensional SSH model, and we don't need any introduction to this community of this model. Only thing is that I want to emphasize that we add a term, this is constant term, diagonal term, just to have this eigenvalues of this is positive definite, because we want to have a non-Hermitian matrix, singular values will be this matrix, square root of that. So it has to be positive definite. So that is why we add and to have a positive definite. So this is the, I don't want to go to this, that are this SSH model. So one can have the block Hamiltonian by taking a Fourier transformation, and this block Hamiltonian is like this, and where sigmas are the Pauli matrices, and this Hermitian model or the singular values has a gap closing at exactly at omega equal to 1. It is SSH model. So this just a moment, I think, yeah. So yeah, so this slide was missing. So we consider actually two model out of this SSH model, and this first model with the T1 equal to 1, T2 is omega, and mu, that extra term we add 1 plus omega. Similarly, and this has a topological transition between nu equal to 0 and nu equal to 1, this model 1. Similarly, model 2 has a topological transition. These are all Hermitian model between nu equal to 1 and nu equal to 2 at omega equal to 1. So model 1, that block Hamiltonian, can be written in this matrix form, and we find that this has a gap closing. That means the singular values gap closes at omega equal to 1, and is omega less than 1, there is gap. Omega greater than 1, there is also gap. There is also, we consider a point omega equal to 34, because we found that some A's by which the Hermitian model is constructed has a EP at around 33. So we also want to that around EP, that Hermitian model, the gaps are not closed. Okay. So what we observed? We observed that a topological knot transition in non-Hermitian system described at A exactly at omega equal to 1. But then this is the knot transition of knot, means the form by the eigenvalues. Okay, and this is characterized by a discontinuity in the eigenvalues. It is not like a transition in EP. EP transition, the eigenvalues coalesce, but here we have a discrete, finite discontinuity that will show in terms of figures. Okay, so again to remind that this is the way. So this is the Hermitian model, SSH2 models, and then this is that non-Hermitian A and A dagger. But if know that this has a gauge freedom, that there are infinitely many A's are possible, which gives rise to the same Hermitian model. Because if you transform A by A times some unitary matrix and you substitute back, then it will be the same H. So our result has to protect by this gauge symmetry that we'll see. Okay, so we have a freedom of choosing a infinitely many E by choosing this V. V is arbitrary. U is of course a fixed related to this H, but this V is arbitrary, so we can have a many choices. So we have the choices of sigma matrices, Pauli matrices as this V. So if we consider this sigma x as V, and we found this is a non-Hermitian A, and this A, now we find eigenvalues, and they have a knot transition, they have a unlink omega less than 1, and for omega greater than 1, they have unknot. So when you go from omega less than 1 to omega greater than 1, there is a eigenvalues knot transition in the non-Hermitian matrix. Exactly same point we have a topological transition in H, the Hermitian model. So this we repeat for many choices, particularly all three Pauli matrices, and we found exactly these changes from unlinked to unknot. So I'm just keeping this different choices, and then those are K independent. Now we found that whether we want to show that this is K dependent choice, only thing that we have to make sure that this V has the same periodicity as our original H, the Hermitian model. So that 0 to 2 pi, the periodicity should be same, and as long as it is there, there will be always a knot transition in the A matrix. But when you have a K dependence, then the knot may be different. Okay. Okay. So so this is for model 1. So this transition with the kappa dependent, this particular choice of kappa that I shown in the transition between nu equal to 1 to nu equal to 2, that are not to Hopplink. So knots are not fixed, but there is a definite transition at the topological transition point. Okay. So now we come to the model 2 and exactly do the same analysis. So this is our model 2, and here we found that for different choices, the transition is unknot to Hopplink. Okay. This model has also, again, there is a gap closing at omega equal to 1 for 3 different values of k, but at the omega 1. And at 67, we also will come back to this point, because this model also A has a exceptional point around 66. So we found that around 66 there is no gap closing. That means there is no topological transition in the Hermitian system. So again, we consider this same exercise of choosing different V's, and we found there is always a unknot to this knot transition. And as long as you take a sigma Pauli matrices, they are always the unknot to Hopplink in this case. But when you take a kappa dependence choice, then this knot structure, knot is different, but transition happens exactly in the same point. Okay, so this is for k dependent Hopplink to, now it's become Hopplink to odd knot. So this knot changes. Okay, now we come to that robustness of our result. So as I mentioned that this construction has a gauge symmetry, A prime going to A plus A multiple W, which W is the arbitrary unitary matrix, then this remains same. So that Hermitian models remain same. So by considering a most general unitary matrix, 2 cross 2, the 4 parameter matrix we consider, and with that we found that gap closing at the point in the Hermitian model where we have a knot transition always. So any knot transition in the non-Hermitian system which correspond to the gap closing, the reverse is true. And any transition, topological transition in the Hermitian system correspond to a knot transition in the non-Hermitian system that is different from a EP transition. It's a discrete, finite discrete transition in the. The converse is not true, that there may be a knot transition in the non-Hermitian system around the EP, there is no topological transition in the Hermitian system. Okay, so this here we have explained that discrete versus so this side is that normal transition which we have found, and this is the EP transition. So let me explain, for this is model 1. So real part of the energy before omega less than 1 has 2 different values, 2 energy levels, whereas the imaginary part was at 0. So 2 real energy eigenvalues. We cross omega equal to 1, the real part becomes same, and we have 2 different. So there is a discrete jump here when we go from cross the omega equal to 1. What happened when EP transition? EP transition, we have the real part is some values, and when imaginary part is same values, and then imaginary part, and but they at the transition point they coalesce. So they coalesce here, but which is, so this is a new kind of phase transition which we discovered in our paper. So this model has a EP as omega equal to 34, where there is no topological transition in the corresponding Hermitian system. Okay, so this is the second model also. I think sorry. This is for model 2, exactly same, so I have no need to explain. Okay, so discrete phase transition that we mentioned, and at the transition point, the eigenvalues have discontinuous behavior, so that we have plotted here, and then this converse is not true for model 2, that also I mentioned. So I have summarized that things in this table. So if choice of V, so if we have a sigma x, then for 0.5 we have unlink, for 1.5 when you cross the omega equal to 1 are not. But when we cross the EP, which is around 33 or 34, then we have a not transition, but in the no Hermitian, no topological transition in the Hermitian model. Similarly, for sigma y, sigma z, we have not seen here EP. So, and for kappa dependent, knots are different, transition at the same point. So, this is also for model 2. Again, we found that the our transition is different, and there is no topological transition in Hermitian model around no gap closing at the EP. Okay. So, this is my conclusion. Conclusion that we have a Hermitian model which has topological behavior, and we construct some non-Hermitian matrix through this relation whose singular values square is the eigenvalues of this topological model. By choosing a appropriate diagonal term, adding a diagonal term, we can consider that. And then eigenvalues of the Hermitian matrix H, this I mentioned. Then topological transition, it has a topological transition. So, implies a not transition in the non-Hermitian matrix A. So, this is a connection between these two Hermitian and non-Hermitian system. Converse is not true, because at the EP we have a transition of knots, but gap is not closing, so no topological transition in the Hermitian model. And this is a first order transition, is completely new to the literature. This is completely different from the transition happening at EP. Okay, thank you for your attention.
Thank you, Professor. Yeah, so floor is open for questions and comment.
So the question is regarding this topological phase transition. So do you associate some topological number also with this topological phase transition, or is it this knot number basically?
No, winding number that I showed, no? We calculate the winding number. It's a one-dimensional model, so we can calculate the winding number.
Okay. The second question is regarding this characterization of the phase transition when you go to the higher dimensions. Like here you are having this knot and this unlinking, two things. So what happens if you go to the higher dimension? Any expectations that you have?
This is very first work. We are trying for higher dimension. Okay. Yeah, we are working on that.
Yeah, so there's one more question.
Can this knot theory can be applied to protein foldings? Protein foldings.
Protein foldings.
Yes.
We have a work in DNA unzipping where we have shown that zipping unzipping transition is actually kind of PT phase transition in a non-Hermitian system. So, protein folding explicitly, I don't know is there any work, but DNA zipping unzipping, we have a physical review e-paper where we have shown it is actually a PT phase transition.
Okay, so last question.
I have a very general informative type of question, like it's not related actually to physics.
No.
You have said there are a huge number of knots till date found. I mean,
Yeah.
so all these are done by hands by mathematician, or is there any computational approach to find those things?
Yeah, of course there are still an open question that any arbitrary unknot, how you can, any arbitrary knot, how you can unknot. So there was a work long ago, so I forgot the name, but I wrote a computer programming, 130 pages. But then it found that algorithm and all this thing, it takes the time they estimate, and it takes the time more than the age of the universe. So to unknot a arbitrary knot.
Okay.
So this is still open. Nobody knows any general method to unknot.
Okay, thank you very much. Let's thank the speaker.